So I called this lesson More Momentum Examples. Why? Because we're going to do some more momentum examples. So again, key ideas, hey, we could even write this right at the top here. We said momentum was equal to mass times velocity. That was our one equation. And then we had the concept of change in momentum, another word for which was impulse. And we said, Matt, you can calculate that two ways. You can calculate that as mass times change in velocity, or you can calculate that as force times change in time, although I get lazy and often don't bother putting a delta in front of time because time is the one that's always a delta. Okay. Which one do you use? It all depends on which information that they give me. So number one says, a force of 8 newtons acts on an object for 10 seconds. The mass of the object is 4 kilograms. What is the object's change in momentum? What's another word for change in momentum? Okay. Well, I'm either going to go mass times change in velocity, or I'm going to go force times change in time. Which one do you think in this question? Which momentum impulse change in momentum equation am I going to use? This one or that one? Look at the information they gave us. I'm going to use force times change in time. Okay, so I'm going to say the change in momentum, the impulse, is force times time, which is 8 newtons times 10 seconds. You know what, Zach? I think even you can do that in your head. What is 8 times 10? There you go. 80 what? Units. Okay, first of all, it can't be newtons because that's force. Kilogram meters per second, although do you remember I also said that a Newton second was the same as momentum? This is where, since technically we used force times time, technically the more appropriate unit to use for momentum would be Newton second. But if you wrote kilogram meters per second, I will not take marks off. But you know me being enough of a nerd that I'll try and have good physics manners. The only other reason I don't like Newton seconds is, first of all, if I just write this, my S's look too much like 5s. Looks like an N5 or anyways. The letter S for me as a lefty is my Achilles heel. My 5s and S's all look the same. What's the object's impulse? This is a trick question meant to take you 1 second. Pardon me? Why is it the answer to A? Because what's another word for impulse? Okay. Or 80 kilogram meters per second. By the way, in Physics 12, those of you that take it, there is a question, and I make it on your test. It's huge. It's very, very convoluted. It's really, really, really wordy. I give all sorts of information, but somewhere in there I mention that it had a change in momentum northeast. Then I give them all sorts of more information, all sorts of changing velocities, and then I ask them, what's the direction of the impulse? And the number of kids that start doing all this complicated stuff and pick the wrong answer would drive me crazy. Really what I'm asking is, do they know that impulse and change momentum are the same thing? It's northeast. A little hint for those who take Physics 12. Hey, what's its change in velocity? Oh, well, another way to calculate impulse is mass times change in velocity. That's also, Dylan, what I wrote right up here, the left-hand side of my impulse equation. Do I know the impulse? 80. Do I know the mass? Oh, yeah, they did tell me. Okay, let's get the change in velocity by itself. How? How would I get the delta V by itself? Divided by M? Okay, so the change in velocity is going to be the impulse divided by the mass. It's going to be 80 divided by 4. Heck, I think I can do this in my head, because 8 divided by 4 is 2, so I think 80 divided by 4 should be 20. You know what a good part D would be? I didn't include it, but I could, because this is the change in velocity, which is final minus initial, I could give you either the final velocity or I could give you the initial velocity and say find the other one. In other words, if you knew the initial velocity was 2 and the change in velocity is 20, what's the final velocity? 22. If you knew that the final velocity was 30 and the change in velocity was 20, what was our initial velocity? 10. So kind of mix and match from there. Number 2, a snow scooter has a mass of 350 kilograms. A constant force acts upon it for 60 seconds. The scooter's initial velocity is 2.5 meters per second and its final velocity is 18 meters per second. What change in momentum does it undergo? Well, change in momentum, or impulse, is written like that, but there's 2 ways to calculate it. Am I going to use the force times time, or am I going to use the mass change in velocity? Yeah, they did give me a time, but they didn't give me the force. In fact, I'll bet you in part B they'll ask me to find the average force. Oh, yeah, there they did. I didn't even have to look. So it's going to be and what's changing anything? Now, you could, don't write this down, don't write this down, don't write this down. You could, if you wanted to, Tara, then go like this, because that's what changing. I prefer, because brackets, I'm more likely to make dumb mistakes on my calculator with brackets and things. I usually just say, you know what, this is final momentum minus initial momentum, because that's really another way to write change in momentum. Right? MV final minus MV initial. Did they give me the mass? Woo! Oh, you can write this down now. Did they give me the final velocity? Did they give me the mass? Woohoo! Did they give me the initial velocity? I get 5,425 kilogram meters per second. And again, Matt, you could also say Newton seconds, but since I didn't use the force one, I use the MV. I'll use my answer, MV, and my units. What's the magnitude of the force? Well, I know that another way to write impulse is force times time, so I guess the force is going to be by the way, I can't remember if I said this yesterday. When we did forces, we said that Newton's second law was this. Don't write this down. Remember that good old F equals ma? I lied to you. Actually, that's not how Sir Isaac Newton wrote it. Sir Isaac Newton wrote his law like that. He was much, much, much more interested in momentum and change in momentum. But you can hopefully see that it actually is F equals ma in disguise. So for what it's worth. F equals ma is easier to remember and it's cleaner. Less intimidating. The change in momentum we said was 5,425. Time, 60. And I get 90.4. What? Newtons. Look at you, front row corner, you're sure. You've been on. Or is it the coffee? It's green tea. Ooh, nice. By the way, the direction of the force, is it in the same direction as the change in velocity or in the opposite direction as the change in velocity? And how can you tell? Yeah.
Same direction, it's positive.
Both have the same sign. Yeah, if they've both been negative, In fact, by the way, the force will always be in the same direction as the change in velocity. What I really should have said is, did you slow down or did you speed up? Because that's really what the force is doing, right? A rocket of mass 2.6 times 10 to the fourth kilograms starting from rest is acted upon by a net force of 2.3 times 10 to the fourth newtons for 120 seconds. What's the final velocity of the rocket? Now, we could do this going winner minus loser, net force is 2.3 times 10 to the 4. We could find the acceleration because F equals ma, and then we can also, though, use impulse. What we could say is this. Did they give me a force and a time? Yeah? That equals what I've just written, Hakeem, is impulse equals impulse. Change in momentum equals change in momentum. This gets us here a little quicker. We can get there in about 2 lines. Oh, what's my initial velocity according to this question?
0.
Ah. Riley, what do they want me to find here? How would I get the final velocity by itself? Divide by, in other words, can you see, I'm getting there in basically a line and a half of work. So although you could, don't write this down, you could have gone and you know, you could have done that too. Can you see, I'm getting there almost, I think, quicker this way. And they're fairly interchangeable. So, if I heard you correctly, and I think I did, you're saying that the final velocity is going to be force times time divided by m. It's going to be, 2.3 times 10 to the fourth times 120 divided by 2.6 times 10 to the fourth. I'm getting a final velocity of 106 meters per second. Anyone else want to double check me? Let me look. Did I type that right? Yeah, 106 units. Hey, it's a velocity, meters per second. So we can even do a little rocket science with this. Where this is really nice is if you somehow knew your final velocity, you had a radar gun or whatever, you can get average force of the engine thrust as well, which is a tricky one to measure otherwise. A car of mass 1,600 kilograms moves at 32 meters per second. Okay. What braking force is needed to bring the car to a halt in 1.6 seconds? I'm sensing a change in speed. I think there's a change in momentum. Let's see if we can solve this using impulse. Let's see if we can solve this by saying, well, impulse equals impulse. You'll notice it's starting with the same equation we did last time. Why? It says bring it to a stop. Oh, and the fact, I think I'm going to end up with a negative kicking around. I think what this is saying is the force being applied is going to be in the opposite direction of your initial direction of travel, which makes sense because that's how you brake. What do they want us? Oh, they want us to find the force? Okay, how do I get the force by itself? Darn right. It's going to be negative mv initial divided by time. It's going to be negative m V initial divided by, I think I can do this in my head, because 1600 divided by 1.6 is going to be 1,000. I think negative 32,000? Double check me. Could be wrong. Negative 32,000? Units? Newtons. What other ways can we apply a force? Oh, fire hose. I don't know if you ever used a fire hose. Any of you ever actually held and used a full-on out fire hose? What do you notice when you make the water go on, by the way?
The thrust of it?
Pardon me?
The thrust of it?
The thrust of it? Which way?
Backwards.
Backward. Oh, that's because forces come in pairs. You're applying a force to the water is applying a force back to you. That water has mass and velocity. It's got momentum. As a matter of fact, fire hoses are used as crowd control in riot situations. If you watch, for example, some of the old civil rights videos, you'll see police turning fire hoses on protesters and literally knocking them off their feet and pushing them along the road. It's really quite horrible. Pardon me? Yeah, the water cannons. Yeah, they're not pleasant, but certainly. Pardon me? Oh yeah. Oh yeah. Not a pleasant. You think, oh, water, it's like a pool. No, it's not. It's not. So let's see. So the fire hose pours 24 kilograms of water each second on a burning building. Water leaves the nozzle at 60 meters per second, assuming the spray does not bounce back from the wall. What's the minimum magnitude of the force on the wall of the building? Well, they want me to find a force. I'm seeing a velocity. I'm seeing a mass. Do you guys see a time anywhere? Sam, you're nodding. Where is it? I disguised it. Do you see, what was the time? Oh, each second. You know what? Our time is going to be 1. That was sneaky of me, but the time is going to be 1. And once again, my pen has died. So I think we can start off again by saying force times time equals mv final minus mv initial. Impulse equals impulse. They want us to find the force. I guess really what I could have done if I'd wanted to right away, Michael, I could have said, you know what? I could divide by time right away to get the force by itself. I'm only seeing one velocity, 60. That 60, is that V initial or is that V final? So what's V final? Oh, I guess it comes to a stop. Yeah. Now we're assuming the spray doesn't bounce back from the wall. If we knew how fast it bounced back from the wall, we would have a V final. Oh, and we would call it negative because it was in the opposite direction of the ingoing velocity, and that would give us a very big force, even more so. So you're saying though that is yeah. Oh, and Sam, why can I do that? Because you pointed out that just equals 1. And does dividing by 1 change anything? Oh, cool. So we're going to have negative because the force being applied is in the opposite direction of the incoming velocity. Mass 24. Velocity 60. 2 times 6 is 120. 1,440? Negative? Newtons. Can you divide that by 9.8 for me? What do you get? 146. So in terms of if we wanted to make that into kilograms, that's like somebody dropping 150 kilogram mass on you if you were a person trying to stand up to this water cannon. You're probably going to move. Number 6. A 4.2 kilogram mass moving at 4.65 meters per second east hits a wall. The wall exerts a force to the west for that many seconds. Find the final speed and direction. Oh. You know what I'm going to do, because I see east and west, and Lord knows I've screwed them up so often, I'll do a little quick compass rose right there. And I might, you know what, I think I'm even going to dollop. I think what we have is, right? And then I think it's going to bounce off the wall. This is what's going on, William, when you play catch with yourself with a bouncy ball against a wall, which I'm assuming most of you have done at least once in your life. Okay, well, I see a force, I see a time. You know what? I think, again, we can say force times time equals mv final. Oh, no squared, Mr. Duick. Minus mv initial. What are they asking us to find here? V final. Are there any zeros in this question where stuff wonderfully cancels? No. Okay. You know what? We can handle this. How would I get the V final by itself? I think the first thing I'd like to do is move this to this side. How? What's sitting right there? What's sitting right there? A negative. I'm going to add this whole thing.
You're going to add the whole thing?
Yeah.
Even though m's multiplying with the
Don't. Well, you know what? This is just like this. 5 equals 3x, because VF is what we're trying to get by itself, plus 9 times 2. Wouldn't you treat that like an 18? Sorry, there's not a plus sign, let's put a minus sign there. I'm going back to math 8 for you. Wouldn't you just treat that like an 18 and plus the 18 to both sides?
Yeah.
So we're going to treat that like one term and just plus the whole thing to both sides. Is that all right?
Yeah.
Make sense? By the way, if you're not sure what to do, when in doubt, make up a number equation very similar, and the math's got to work. So I think we're going to get this. Yeah? Okay. What are we trying to find?
Are you supposed to get rid of math?
I don't know. What are we trying to find? Oh, how would I get the VF by itself? Okay, so I'm going to now go divide by m. I'll divide this whole thing by m. Now the masses aren't going to cancel because I don't have a mass in everything on the left-hand side. But I'm going to get this. The final velocity is going to be the force times time plus the mass times the initial velocity, and then divide that whole thing by the mass. Okay. Can do this. What's the force?
4.2.
That's the force?
Oh, no. 350.
Now, I'm going to be fussy. I'm going to say, actually, you're wrong. It's not 350. Why does it have to be negative?
Going off.
The third word after Newton's. Okay, they specifically said, now, by the way, you could let the force be positive. If you do that, though, if you let west be positive, which way had you better let east be? Negative. I don't care which one you do. Usually we're kind of used to the right being east being positive and the left west being negative. So Riley, let's stick with that. We're going to call this a negative 350 times the time, 0.075. Scalar, so I don't care about direction there, plus the mass, hey, that's a scalar, 4.2, times v initial. Okay, I got directions. I got to be careful. Is this a positive or a negative velocity? East, I'll keep it positive, 4.65. All divided by the mass, 4.2. What is the velocity? Let's go see. Negative 350 times 0.075 plus 4.2 times 4.65, and all of that is, 4.2, Mr. Dewick. Caught myself. And all of that should be in one big bracket because it's on the top. Divided by 4.2. Oh, get negative 1.6? You know what? It said find the final speed and direction. So instead of saying negative, let's go like this. 1.6 meters per second direction. Gotta be. Oh, it bounced off the wall back in the direction that it came. Which seems really obvious now, but there, we proved it. I guess what that means then, Tanisha, is if you crash into something that doesn't move and you bounce off of it, it must have applied a force in the negative or opposite direction that you came in. That's the other way to think about it. If you know you bounced backwards, then the net force was in the opposite direction. That's also what's going on when you try and tackle somebody. You're trying to apply a force in the opposite direction as well. Is this last one, rifle? Sure. Let's fire a gun. A rifle accelerates a 12-gram bullet, accelerates 12-gram bullets from rest to 250 meters per second. The rifle barrel is about 0.85 meters long. Find A, the impulse acting on the, okay. Impulse, well that's change in momentum. Which one am I going to use? Yeah, I don't see a force. In fact, I don't see a force or a time. So I think I'm going to go mass V final minus mass V initial, mass times change in velocity. Conveniently from rest, mass. Don't put a 12. Bullets don't weigh 12 kilograms. Holy smokes. It says 12 grams, which is point what? Yeah, there's 1,000 grams in a kilogram. Velocity, 250. Uh, 12 times 25. Is it 3? Even? So I'll go 3.0 to give it like a 2 sig figgy feel. In fact, really I should go to 3 sig figs because the 250 is to 3 sig figs and the 12.0 is to 3 sig figs. So 3.00 kilogram meters per second. B. What are they asking us to find in B? Oh, well, you know what? I'm going to say that change in momentum equals force times time. Hey, this is easy, Mr. Dewick. The force is going to be the change in momentum from part A divided by the time. So oh. Did they give me the time? Apparently that means they think I can figure out the time. Well, we've gotten good at this by this time of the year. What else have they told me? What haven't I used yet? I think even though technically they're asking me to find the force in part B, I'm going to spend most of my time finding time. No pun intended. So I'm going to write down D equals 0.85. I agree. What else do I know? Oh, V initial equals, hey, this is a great review. V final equals 250. Yeah.
Could you use force equals MA for this, since we're given the acceleration?
I was given the acceleration?
Right.
But if they give me the acceleration, yeah, I would go F equals ma. And that, by the way, that's why I didn't give it to you. So F equals ma. A couple units ago, we handled that in our sleep. Now I'm saying, you know what? I don't always have to give you the A. We're broadening our... well, I'm going to write down T equals, don't know. Have I got an equation that has V final, V initial, D, and T in it? Huh? You caught yourself, right?
Yeah.
Dope. Have I got an equation that has D? I think I do.
D is equal to half.
The one that we almost never used. The whole D is equal to 1/2 VI plus VF times T. Although, Tanisha, I'm going to argue that I can do that because VI is 0. You with me so far? In which case, I'm going to rewrite this as D equals VFT, and instead of a 1/2 in the front, isn't that the same as just dividing by 2? And to me, that looks way less intimidating, because now I can say, well, how would I get the T by itself? Well, what would I do with the VF? Divide. What would I do with the 2? AJ? Times. Okay, so T is going to be 2 times the distance divided by V final. 2 times 0.85 divided by 250. Yeah, 250. Do that one in your head, Mr. Dewick. Okay, fine. That one's a bit beyond me. 0.0068 seconds. Is that reasonable? Yeah, bullets travel down barrels of guns pretty fast. Like if I got an answer of 6.8, I'd be going, and even if I got an answer of 0.68, I'd be saying, you know what, half a second is about that long. I don't think it takes that long for a bullet to leave the barrel of a rifle. So this seems okay. Now, let's go plug it in at the very, very top. This is going to be, change in momentum was 3 divided by 0.0068, 6.8 milliseconds. 3 divided by that, I get 441 newtons. I'll put a box around this as my final answer because I did a lot of work below it. Zach, the whole point of today is, okay, you know what? That impulse, the fact that I can write it 2 different ways, it's pretty flexible. I got to be a little clever. I can't claim this is walk in the park, plug and chug easy. I'm not going to say that. I got to think and scratch my brain a little bit. But if you wrap your brain around it, you can do some nice stuff. What's the homework? Homework. I gave you this sheet intelligently entitled Momentum and Impulse, because that's what we just looked at. It says, please answer each of the following with the proper units. And most of this, be clever. I don't think there's any really weird ones. I kind of, and there's scrambled answers. And then I got some challenge questions. These ones I don't have the answers attached for. So where it says momentum and impulse challenge questions, how do seatbelts and airbags protect car drivers in a collision? We talked about that yesterday, but you can refresh your memory. Tree car crash, wall, rifle. Oh, I did something like this with you guys, it turns out. Pinball is a great example of a momentum question because the pinball flipper, applies a force to the ball, or a bumper applies a force to the ball. Planes taking off. So that's what you can work on, but I have a little video to show you first.